In this video, we're going to continue our work with differentiation and look at an introduction to stationary points. In the last video, we looked at increasing and decreasing functions. So this is the graph that we had. We can see that the gradient of the function in this particular interval is going to be negative. So we can say that this is a decreasing function just here. If we took the derivative f dashed of x and evaluated it, it would give us now a value less than 0, or if you like, dy by dx, the gradient function, is less than 0. At this point just here, we have a 0 gradient, and we call this a stationary point. At a stationary point, f dashed of x will be equal to 0, or if you're using dy dx notation, dy dx will be equal to 0. So for all stationary points, the gradient will be 0. If we now look to the right, we have an increasing function. If we looked at the gradient here, we could say f dashed of x is going to be greater than 0, or if you like, dy by dx is greater than 0. Again, this point right here, we have a 0 gradient, and we call this a stationary point. If we now look to the right, we've got a negative, negative, negative down to this point right here. And again, we have a 0 gradient or a stationary point. Let's now move to the right, and we've got a positive gradient right the way up, like so. We keep coming up, we keep coming up right here. Now this one is slightly more subtle, but we have now a 0 gradient just here. So if I drew a tangent to the curve at this particular point, the tangent would be horizontal or parallel to the x-axis. Then what we're going to do is look at the gradient now to the right, and that is going to be positive. So let's go ahead and look at drawing some tangents. So this one, like so, we'd have this one, and then we'd have this one, and we'd have this one. So these are all stationary points. What I'm now going to do is determine their nature or classify them. What we can see here on this particular one is that the gradient to the left is negative, and then we have now a positive gradient to the right. We call this a minimum point. So this one just here, and let's write that on. This one is going to be now a minimum. So that is a minimum. Or it opens upwards, or if you like, it's concave upwards. What I'm now going to do is look at the gradient here. Now the gradient here is positive. We come up to the 0 and we come round, and it's now negative. This one opens downwards, and we call this now a maximum. You might hear these being referred to as local maximum and minimum points. So that is a maximum. This one at the bottom, again, we've got a negative gradient, we've got 0, and then we've got a positive, and this one too is a minimum. So what we're going to write now is minimum just here. The next one is slightly different. What we have is a positive gradient to the left, we're stationary, and a positive. This is called a point of inflection. So if I just draw that, now we'll just change the colour. What we have is positive, 0, positive. We could have negative, 0, negative. It's just the sign, either side is going to be the same. So this now is a point of inflection. So point of inflection. So let's go ahead now and look at how we find stationary points and how we use the second derivative test to determine their nature. This one is a minimum, and what I'm going to do, I'll just draw this up, and I'm going to put the conditions such that we have a minimum point. Then we will look at a maximum, and then we will look at a point of inflection. When you take the derivative and evaluate it for all of these, that is going to be 0 if it's stationary. So let's start with a minimum. So this is a minimum, so it opens upwards. Think of a standard positive quadratic graph. We got negative, 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 0, positive, 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 and we write minimum point. For minimum point, f dashed of x is 0, or if you like, dy dx is 0. And we can say at this point, the second derivative, and the notation we use is f double dashed of x is going to be greater than 0. Or, using the notation for dy dx, the second derivative, we write and say as d2y by dx squared, and that will be greater than 0. So these are just interchangeable. Let's just look at this in action. So let's take a quadratic function. Let's say we've got y is equal to, let's go for, we'll go for x squared minus 2x, and then we'll have plus 5. What we're going to do now is look at finding the stationary point and determining its nature. So dy dx will be equal to 0 for a stationary point, so for SP. Therefore, what we can say then is 0 is going to be equal to 2x minus 2. So we can see the x-coordinate of the stationary point is 1. To find the y-coordinate, we simply substitute in. So that'll be 1 minus 2 plus 5. So that will give me that y is going to be equal to 4. So the stationary point has the coordinates now 1, 4. Let's now look at determining the nature. d2y by dx squared, the second derivative, is simply going to be the derivative of 2x minus 2. Remember, taking the second derivative, we're differentiating again. That gives us the constant of 2. Therefore, we can say this is a minimum as now the second derivative d2y by dx squared is greater than 0. You're probably shouting at the computer screen saying, why didn't you complete the square? Absolutely, we can complete the square to find a maximum or minimum point of a quadratic function. That won't work though for a cubic function or some other polynomial. So we have the choice of either completing the square or using differentiation. Hopefully you can see now that this is why we would use differentiation as an alternative. So let's look at a maximum. A good example of this again is a parabola, and this time a negative quadratic. So we got a positive gradient, we got a positive right the way up now to a 0 gradient, then a negative. The conditions for this to be a maximum, as always, if it's stationary, f dash of x will be equal to 0, or if you're using dy dx notation, dy dx will be equal to 0. We can say that the second derivative test, f double dash of x, this time will be less than 0, or if you like, d2y by dx squared is less than 0. Let's just talk about this second derivative. The second derivative tells us if the first derivative is increasing or decreasing. So shortly I'll show you a graphical representation of this, but if that seems a bit strange, it's the rate of change of the rate of change. So it's saying how is the gradient changing? Now let's go back to a quadratic. So let's now take a negative quadratic. So let's say f of x, and I'll use f of x. F of x is equal to negative, let's go for negative 3x squared plus, let's go for plus 12x plus 1. So what we want then, we'll find the stationary point. Remember, this is going to have a stationary point. It'll have that point right there. And then we will say f dash x will be equal to 0 for stationary point. So I'm showing whoever's marking my work, I know what I'm on about. Therefore, 0 will be equal to, and this will give me now negative 6x plus, what's that going to give me? Plus 12, and then plus 0. So from this, the x-coordinate is going to be positive 2. So if I wanted the y-coordinate, I'd simply substitute in. So what's that going to give me? 12, 13? A quick guess. I'll let you check that. I've just subbed that in mentally. That's going to be negative 12 plus 24, which is 12 plus 1. I'm hoping that's right. So let's now determine the nature. So f double dashed of x, if we look at an expression for that, that is going to give us now, it's the derivative of this, which is negative 6. Therefore, we can say this is a maximum as f, and just writing this in, f double dashed of x is going to be now less than 0. This isn't always going to be a constant. You can see these terms are independent of x. If they're not, we simply substitute in the x coordinate. So for example, if this was negative 6x plus 2, I would do f double dash of 2 to evaluate that. Let's just show that in action actually. Let's take a cubic function. Let's make this nice and straightforward. So y is going to be equal to, let's go for 1/3 x cubed, and then we'll go for minus 1/2 x squared, then we'll go for minus 12x, and we'll have plus, let's go for plus 6. So dy dx will determine the nature of the stationary point. So we'll find the x coordinate of the stationary point. I'm not going to find the y coordinate because that would mean subbing in. I'm just going to find the x coordinate, and then we're going to determine the nature of these. So that's going to give me now x squared minus x minus 12. So for SP, we can say now dy dx will be equal to 0. Therefore, 0, and I'm just going to factor this. What we're going to have x minus 4, and then we're going to have x plus 3. So we can see that x will be equal to 4, or we've got x is equal to negative 3. So if you wanted to find the y coordinates, you could go ahead and substitute in. What we've got here is a scenario, and I'll just draw a quick sketch. Let's just draw a quick sketch. So with a cubic, we're going to have a maximum of 2 stationary points. Let's say it looks something, and this really is just a sketch. Let's say it looks something like that. Let's go for that. So what we've got, in fact, let's just move this axis across to make it right. We'll go for that. This point right here, let's put this on. The x coordinate just here, and we'll put that there. X is going to be equal to negative 3. Find the y coordinate if you want, and this point right here, x is going to be equal to 4. These are the points on the curve where the tangent to the curve is going to be parallel to the x-axis. So let's just put that in there. What we can do is determine the nature of these. Now I knew that cubic equation would start in the third quadrant and leave in the first and have this particular shape. We can see that this is going to be a maximum just here. This is a max. We can see that from the nature of it. We've got positive, 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 0, negative, negative, negative. This just here is a min. So that is a min, and we can see that this is negative, 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 0, positive, positive, positive. So increasing to decreasing, decreasing to increasing. But let's go ahead and determine the nature of those, because we might not be able to sketch this. It might be a function that we don't yet know. So let's take d2y by dx squared. This is the second derivative. So if I look here, that's going to give me now, the derivative here is going to be 2x minus 1. So when x is equal to negative 3, d2y by dx squared is going to be equal to 2 lots of, what's that going to be? 2 lots of negative 3 minus 1, that's negative 7. Therefore, we can say that's a max, as it's less than 0. So you can see this time I've substituted in. So if that was f double dashed of x, we would do f double dashed of negative 3. If I look at the next one, so when x is equal to positive 4, d2y by dx squared will be equal to 2 lots of positive 4 minus 1, that's 7. Therefore, it's going to be a minimum as the second derivative. When we evaluate it with the x coordinate of the stationary point, it's greater than 0. It's a coincidence that these values right here are the same numeric one. Again, don't read too much into that. So there we go, that's finding and determining the nature of a stationary point. Let's look at our last one, and these ones are slightly, this is slightly more interesting. A point of inflection. A point of inflection now has the same gradient either side. So what we'll have is a 0 just here, positive, 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 and then we'd have positive, positive, positive. Now it won't necessarily be positive either side, it might be negative either side. As long as the sign is the same, it's a point of inflection. So this, for example, negative, 0, negative, 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 negative. With this particular example, what we're going to have is, as always, when we take the first derivative, f dash of x, it will be 0, or dy dx is equal to 0. This is the slight letdown here. The second derivative test is inconclusive. It doesn't tell us about the behaviour of f of x. So f double dashed of x will be equal to 0, or if we like, d2y by dx squared will be equal to 0. If now, or if this scenario occurs, what we need to do is further investigation. So we saw before, if it's greater than 0, we had a minimum, less than 0, we had a maximum. Now we've just got to consider investigating further, as it's inconclusive. What we can say about a point of inflection is that f triple dashed of x will not be equal to 0, or if you're using the other notation, d3y by dx cubed will not be equal to 0. So this is the condition. Let's just take a function. So let's say y is equal to 4x cubed. So dy dx will be equal to 12x squared. So for stationary point, for SP, we can say now dy dx is equal to 0. Therefore, on here, we can see 12x squared is equal to 0 and x is 0. And that's similar to the graph that we've got here. That's fine. Okay, let's now take the second derivative to determine its nature, d2y by dx squared. Well, that's going to be 24x. We can say when x is equal to 0, which is a stationary point, d2y by dx squared will be equal to 0. So this is inconclusive. At this particular stage, if we take the third derivative, d3y by dx cubed, we can see that the derivative for 24x is 24. Therefore, it is a point of inflection. So point of inflection, I'm just writing this in, as the third derivative is not 0. And that is how we would do it. Alternatively, if we wanted to do this, as long as we pick now a very tight interval, we can evaluate a point either side of the stationary point. It certainly helps if we have it graphically to see. The only issue with this is if we have two stationary points that are very close, if the interval isn't tight enough, we can make mistakes. So let's now look at the gradient when x is equal to now negative 0.1 and look at the gradient of the function when x is equal to 0.1. The reason I'm choosing these in my function just here is that it will evaluate the gradient if I put these into dy dx. So I know the stationary point of the one we've just found is 0, so I'm going to test a point either side. So what I've got then, and if I just write this up, we'll write this just up. We've got x is equal to negative 0.1 and x is equal to positive 0.1. So if I look now at my function here, which we will say is this one, if I substitute in dy dx when x is equal to negative 0.1, dy dx is going to be equal to, what's that going to be, 12/100ths, which we could of course simplify. The main thing here is that that's a positive gradient. Now if I substitute in and evaluate the gradient, that's what dy dx does, it's a gradient function. When x is going to be 0.1, that too is going to give us 12/100ths. And we can see that this too is positive. So what we have is a positive gradient either side, so we can say that it's a point of inflection. So that's an alternative approach. So there we go, finding stationary points. To find a stationary point, all you need to do is set the derivative equal to 0, solve for x. If you want the y coordinate, plug it back into a function, and that will give you the y coordinate. Don't put it back into the derivative, as you're going to end up getting 0. Then if you want to test the nature, second derivative test. Differentiate again. If when you evaluate the x coordinate of the stationary point at that point, then we would end up now with it greater than 0 if it's a minimum, less than 0 if it's a maximum. It would be equal to 0 and inconclusive, so we would need to do further tests, and then if the third derivative was not 0, it's a point of inflection. Okay, now I'm going to just do this bit for completeness. If you find this slightly mind-boggling, that's perfectly fine. What we've got here is a cubic function, and we can see there's a maximum just here and a minimum just here. What I'm going to do is put on the gradient function. The gradient function of a cubic will be a quadratic. If we look just here, where the x-coordinate is 1.423, we can see that the gradient of the derivative, so this, remember, is f dash of x, given f of x, the gradient of f dash of x, or f double dash of x, would be negative. If we look at this point just here, and that is going to be my minimum point, we can see the gradient of a function at that point, the gradient of the derivative, is going to be positive. So if you're wondering why, for a maximum, we have now a second derivative that's negative, there's your reason. And if we wanted to know why when we have a minimum, the second derivative is positive, that's your reason, because we're looking at the gradient of those points. I've actually gone ahead and taken the second derivative, and we can see that this right here is going to be negative in this particular interval and then positive in this one. I had concerns or reservations about putting this on because some students, when they see this, would like to think that that's a tangent, but it isn't. It's the second derivative. So if you evaluate now the second derivative at this particular point, we can see we're going to get a negative value. F of x, f dash of x, f double dash of x, y, dy dx, d2y by dx squared. So hopefully that gives you some graphical representation of what's going on. You might find it easier just to consider the gradient of the gradient. So that was done for completeness. Let's just go ahead and work through some basic questions before we move on to a range of questions in a later video. So what we've got here, question 4. Below is part of the graph y equals g of x. In part A, we're asked to label the stationary points on the curve A and B, where B is greater than A. So nice and straightforward. We're not given a function, so this is just doing it purely graphically. We can see that these 2 points are where we're stationary. So if I drew a tangent to the curve just here and a tangent to the curve just here, that is where we would have now the stationary points. So we can say now that B is going to be just here and A is going to be just here, as we're told now that B is greater than A. So this is going to be now B, this is going to be A. In part B, we're asked to determine the nature of the stationary points A and B. We're going to do this graphically, so we have no function to differentiate, but we should be able to see that we have a negative, 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 0, positive, 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 and this is a minimum point. It opens upwards, so that is a minimum. Here we've got positive, 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 0, then we've got negative, negative, negative on here, and we can see that this is going to be a maximum. It's opening downwards. In part C, we need to explain why A and B are not points of inflection. We can say that the gradient either side of the stationary point changes. With a point of inflection, the gradient either side of the stationary point will be the same. In part D, we need to draw a tangent to the curve at any point where the function is 1 increasing and 2 decreasing. So let's do a point where it's increasing, nice and straightforward. That's an increasing function there. It's decreasing just there, and I could go ahead and label those up. It's decreasing just here, and we can see it's increasing just there. So I put those up and label them. So nice, straightforward, just a bit of an introduction, and as stated, the more challenging questions will come up in the next video. In question 5, it says use differentiation to show that the coordinates of a stationary point on the curve y is equal to x squared minus 8x plus 6 are 4, negative 10. So all I'm going to do is write 4sp dy dx will be equal to 0. So y is equal to x squared minus 8x plus 6. dy dx will be equal to differentiating the quadratic 2x minus 8. We can say 0 is equal to 2x minus 8, and then solving for x is equal to 4. Subbing back in, we can say that y is going to be equal to 4 squared minus 8 lots of 4 plus 6. So what's that going to give us? Plus 6 just here. That's going to give us 16 plus 6 minus 32, which is going to give us now negative 10 as required. So all I've done is substituted that in and found the stationary point. Show that this result is true by completing the square to find the stationary point. So completing the square is an alternative method to find either the maximum or minimum point of a quadratic equation. So if I complete the square, y is going to be equal to now x minus half the coefficient, which is going to be minus 4. We need to square. We subtract away 16 and we add the 10. We can see that y is going to be equal to x minus 4 all squared, and then we're going to have on here, now that's going to give me minus 10. Therefore, we can say now that 4 comma negative 10 is stationary, so is the SP. So that's an alternative, and you might say, well, it's easier to complete the square with a quadratic. Perfectly fine, up to you. Can't do it with a cubic function, and certainly wouldn't want to try and do anything with a cubic function and another polynomial. Okay, in this one, determine the nature of a stationary point by sketching the graph of y is equal to x squared minus 8x plus 6. So let's just go ahead and draw that. So this should be relatively straightforward. Let's do that. So we'll have something that looks a bit like this. Not fantastically accurate. This point is going to be 4 comma negative 10. This point is going to be 0 comma 6. We can see now on here, and I'll just put these on, just popping this on, that's going to be negative, 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 0, positive, positive, positive. Therefore, it's going to be a minimum. So that is a minimum. In part D, we need to show that our answer to part C is correct by evaluating the second derivative at x is equal to positive 4. So what we've got, we know, and we've written this out here, we've got that y is equal to x squared minus 8x plus 6. We can say now that dy dx is going to be equal, as we saw, 2x minus the 8. d2y by dx squared will be the derivative of this, which is 2. We can say now 4 min, so 4 min d2y by dx squared will be greater than 0. Therefore, we can say that 4 comma negative 10 is a minimum. So is a min. The only reason these questions are included is that you can get some concept and you can relate to them a lot easier. So you've seen these in the past. In the next video, the questions that we do, you probably won't recognize some of the functions, but hopefully this has given you a good introduction to those stationary points and how to determine them. So yeah, next video we will look at some more challenging questions, but hopefully that has helped out on finding stationary points and determining their nature.